Yes, welcome to Mark 101.
We should trademark it, and anytime anybody does anything, since it involves physics, they have to pay you for using your laws.
You've broken one of my laws.
Yes. No, you can't. The laws of it. Human laws are really just really strong suggestions. As far as we know, physics laws are not strong suggestions.
Laws are simple guidelines.
Who would like guidelines? All right, so last time we were talking about how if you look at the Boltzmann equation and you have a gas of neutral hydrogen atoms, that it takes a temperature of 86,400 Kelvin to get equal numbers in n equals 1 and n equals 2, the ground state and the first excited state. And then we said, but wait a minute, how come then the strongest hydrogen lines are in stars of around 10,000 Kelvin? Why doesn't making them hotter make the Balmer line stronger? Because the fraction of atoms that are in n equals 2 keeps getting bigger as you increase the temperature. And the answer was because you start to ionize the atoms so that they don't have any electrons whatsoever. The Boltzmann equation is telling us of the neutral atoms, the one that actually have electrons, what's the ratio of the number that have the electron in n equals 2, first excited state, versus the number that have it in the ground state. But as the temperature increases and collisions become more frequent and more violent, you strip electrons off of the atoms. And so by the time you're at 86,400 Kelvin, it turns out you're essentially completely ionized. So there aren't any neutral atoms to which the Boltzmann equation is really applying. It's kind of a red herring. So now we have to talk about ionization. So we will talk about the Saha equation. Yeah, that kind of right. We've got and remember that, you know, versus Saha for this equation. So remember that we said the greater the ionization energy chi sub I, the smaller the fraction of atoms that will be ionized. Let's continue here. So chi I equals the ionization energy chi I is the ionization energy is the energy needed to take an electron from the ground state of the atom and ionize. It's the minimum energy needed to ionize the ground state and produce the next ionization stage. And the atom may not have been in the ground state. If the atom's in an excited state, it doesn't take as much energy to ionize it, so we have to avoid accounting for that. Chi I, the energy, the ionization energy, is the energy needed to go from the ground state, lowest energy state, of ionization stage I, and here I is the number of electrons missing. Since we're astronomers, of course, we use a Roman numeral for that, which is one more than the number of electrons missing, whatever. To the ground state of ionization stage I plus 1. Ionization stage I plus 1. Notice I'm not saying you actually are pulling the electron out of the ground state orbital. I mean, by the ground state, the overall configuration where you dump all the electrons in the lowest energy orbitals still available to them. So, in general, what we're talking about for the ionization energy here is you're pulling the electron that is in the highest energy occupied orbital, the one that is closest to being free anyway. You strip that one off, and you leave behind all the other electrons in their lowest energy orbitals still. So you're going from the ground state to the ground state of the two ionization stages. But of course, the initial and final states might not be ground states. You might be going from an excited state to an excited state. However, the initial and final states may not be these ground states. To take account of this, we need what's called the partition function. Have any of you guys taken thermal yet? Nope. Nine. Ah, okay, fine. So, good. From that, if you've taken it, it'd be good. This will be familiar to you. Since you haven't taken it, it's good. When you see this in StatMech, you'll say, oh yeah, I've done some of this before. Of course, you'll do it in more detail here, but to take account of this, we need the so-called partition function. And we use a capital Z to stand for the partition function. And ever since I took German in high school, I've made my Z's with crossbars. So capital Z is the sum from I equals 1 to infinity of, okay, that has to be a J. The sum from J equals 1 to infinity. You don't have to erase anything, just put a little hook on the bottom of your I, right? J equals 1 to infinity of G sub J, the degeneracy of the Jth ionization stage levels, e to the, no, wait, what am I, do I want that? No? Okay. What am I doing? What do I want that index to be there? It's got to be, yeah, it's got to be a J. Yeah, okay. E to the minus E sub J minus E sub 1 over KT. So E sub 1 is the ground state energy. So in other words, for all the different levels in my given ionization stage, so later I'll put like a Z subscript here to mean the partition function for a given ionization stage. But generically, a partition function has the form. It's the sum over all of the energy levels of degeneracy of the energy level times e to the minus difference in the energy, but difference in the energy of that level and the ground state over KT. Remember, KT has energy units, so it's the fraction of KT by which the energy exceeds the ground state for each of the exponents in the exponential here. And it can be convenient because notice that the first one's going to be E1 minus E1, so it'll be e to the 0, to just separate off. The first term is always the degeneracy of the ground state, plus the contributions from all the other energy levels. J equals 2 to infinity. Gj e to the minus Ej minus E1 over KT. So sometimes we explicitly separate out that first term to note that it's always the degeneracy of the ground state. How many states have the same energy when we're talking about the ground state? Yes?
Why do they put a negative instead of just switching to U1 minus EJ?
Because Ej minus E1 will be positive. So in other words, the idea is you're looking at higher energy levels, so they have higher energy than the ground state. So yeah, you could switch it around, but this kind of emphasizes that these E's are to negative powers. So they're getting smaller and smaller as you go up the energy run, so to speak. It's just to emphasize that fact.
but all, the surfactant's always gonna cancel the negatives.
Yeah, right, yeah. So in other words, yeah, I could write it as e to the plus e1 minus ej. But this is just making it more explicit because by putting it in this order, the difference in energies is positive. Every state has more energy than the ground state, so these differences are all positive. And the minus sign there then emphasizes these are negative quantities. They'd still be negative quantities, of course, if you made it e1 minus ej, because you'd be subtracting a bigger number from a smaller number. This is just to emphasize you're adding up smaller and smaller quantities because the exponents are becoming more and more negative as you increase the energies. That's, so it's just a convention. Could have done it the other way, but we like to do it this way. Okay? So, here's a problem. In general, Z diverges. In other words, if I actually form that sum, I get infinity. That's too big. So consider hydrogen, right? Remember the hydrogen energy level diagram, we have n equals 1, 2, 3, 4. What's E sub n for hydrogen? Minus 13.6 eV divided by n squared, divided by n squared. So E sub n approaches a finite limit, namely 0. It goes to 0 as n goes to infinity, and then the ground state is 13.6 electron volts below that. So chi for hydrogen is 13.6 electron volts because to ionize it from its ground state means strip the electron out of the ground state, right? Strip the electron out of the ground state. The ground state energy is minus 13.6 electron volts, so you have to add 13.6 electron volts to produce the ground state of the ionized hydrogen atom, which you would think of as being that the proton and the electron are at rest when we're done. The lowest energy configuration for when you are done.
So car value is always going to 0? Is that what it is?
No, not necessarily, because in general, this is for hydrogen, right? So, but if I had something like helium, then what I mean is that, well, yeah, okay, yeah, yeah. So, look at it like this. Okay, suppose, so, I'll say a couple of things. The chi refers to the minimum energy needed to strip the electron and leave the result, and the result has to be the lowest energy configuration of the next ionization stage. So for a hydrogen atom, one electron, the lowest energy configuration after ionization is the electron is at rest, the proton is at rest, so that takes 13.6 electron volts. That's not the only possibility. For example, suppose the hydrogen electron was in n equals 2 before we started, and you strip it out of n equals 2. How much energy does that take?
13.6 divided by 4.
13.6 divided by 4, so that only takes 3.4 electron volts, right? So in other words, when we talk about reionization energy, we mean from the ground state. The partition function accounts for it in real gas. Some of them will be in n equals 2 before they get the electron stripped. Some of them will be in n equals 3, and so on and so forth. That's why we have the sum over these values here, because if it's above the ground state, it's not going to take as much energy to strip it as if it's in the ground state. Now take a helium atom, okay? So if it is in the ground state, then both of the electrons are in the 1s orbital. And if you want the ground state configuration of the next ionization stage, for helium, you strip the electron out of the ground state orbital and leave it at rest. You don't want any extra kinetic energy that you have to give the electron. What does the leftover atom look like?
So it's one.
It's got one electron in the 1s orbit, right? But what if one electron was in the 1s orbital and one electron was in a 3p orbital? That's not going to take as much energy. You're just removing that from the 3p orbital. Also, what if you had this collision that had multiple effects? It bumps the electron. You start out with the helium both, say, in the 1s orbital. Collision comes along. In principle, it could bump one electron out and leave it at rest, and the other electron managed to get bumped up to 2s, which is a higher energy state, and so forth. So there's all these different possibilities for the before state and the after state. When we say the chi for hydrogen is 13.6 eV, that's referring specifically to ground state, or ground state for the stripped off electron, a stripped off proton, it's at rest, the electron's at rest, 13.6 eV. So the energy is 13.6 eV. The minimum energy it takes to ionize it if it's in the ground state is at 13.6 eV. Remove E line, remove the electron from the ground state orbital. And have electron and proton, P, at rest afterwards. If you give it more than 13.6 electron volts, they'll be moving after ionization. So if we look at the partition function, in this summation, E sub j minus E sub 1 is approaching the limit, 13.6 electron volts, as j goes to infinity in the summation. So you're doing the summation from j equals 1 to infinity. As j goes to infinity, all those exponentials are approaching e to the minus 13.6 electron volts over kT. That's a finite number. So you're adding a bunch of finite numbers together. And furthermore, what's G sub j for hydrogen? What's the degeneracy for energy level J? J here is standing for the principal quantum number, even though we usually call that N. Here we're calling it J because we're summing over the states and calling them J. Normally we call it N for hydrogen. The degeneracy for hydrogen is what? 2J squared in this case, right? The degeneracy is 2J squared. Okay, so basically in our sum, j equals 1 to infinity, we're getting, so z is equal to the sum of 2j squared e to the minus ej minus e1 over kt. What's that do as j goes to infinity? Blows up good. That blows up good. And meanwhile, that goes to a finite limit, e to the minus 13.6 electron volts over kT. It's not going to 0, it's going to some finite limit, e to the minus 13.6 electron volts over kT. So I'm just adding bigger and bigger terms. 2j squared is getting bigger and bigger as j goes to infinity. This essentially is staying the same, so I'm adding bigger and bigger terms. So if I really take that sum all the way out to infinity, it's going to blow up, right? So it blows up. How does it blow up? Good, yeah. So the sum blows up good. I don't even know what that's from. That was from some TV show. We're gonna blow it up good or something, you know.
It probably reminded you of the monster truck rally.
That's right, yeah. Yeah. We're gonna blow our truck up good on the floor of the Coliseum, which is gonna be a giant ball. Damn, that would be an awesome show.
They've been advertising it to us wrong.
You'll hire me.
You need to take those from monster truck rallies.
Yeah. Okay, so anyway. So, we got a problem here. How do we avoid this problem? We've already mentioned it. And that is that, yeah, we're summing up to infinity nominally in the partition function, but in the real world, you also have to include the fact that for very large, for hydrogen, for example, for very large values of the energy, it's not likely to exist because the atom would be so large that a collision will just bump the electron off anyway. Hydrogen atoms a meter across cannot exist in an actual gas of atoms. And we really need to add over the states that actually exist in some sense. So you don't really carry the sum out to infinity. So we'll put it like this. However, the orbital radius goes to infinity as j goes to infinity. Really, by that we mean the expectation value in quantum mechanics, but whatever. The orbital radius goes to infinity as j goes to infinity. So only for an isolated atom alone in the universe could all states contribute. But you know what? That isolated atom would just be sitting in its ground state, so who cares what the partition function is? In a stellar atmosphere, collisions eliminate most of the states. Really, we need to multiply each term in the sum by the probability that it has not been, quote unquote, perturbed out of existence. Which means that actually calculating partition functions is something of a high art. And so we're often going to say, and the experts calculated the partition function, and here it is. Really, we need to multiply each term in the sum. By the probability that it has not been perturbed out of existence. To perturb is basically to disturb. But physicists, for some reason, well, physicists like to say perturb. has not been, quote unquote, perturbed out of existence. In many cases, the connotation is a perturbation is a small disturbance. Here, there's not really such a connotation. All right, I plugged in the speakers instead of the laptop, so it went sleepy. That's the technical term.
Yeah.
Yeah. Where'd you go? It's feeling blue. Oh, there we go. Not that that's relevant right now, but anyway. So now we're ready to write down the Saha equation. And do I still have that in here? We should. No, I don't. I took it out apparently. But anyway, in my notes here, I don't have it in there. But one time, at one point I said, you know what? I should see if I can derive the Saha equation. So I did. So I put it in the notes. So I was kind of proud of that. I should put it back. You have to know thermal to understand the derivation.
You should put that in the extra 110 lecture.
Yeah, that sounds good. Yeah, so now we'll derive the Saha equation. Where is everybody?
I'd like to see that as one time, like sitting on one of the lectures and just go from like, now that you know conceptually, here's the math, and just push down the board, it's all math.
Yeah.
Write this down.
I'd just be like punking the whole class basically. It's like,
I think like 75% would just stare at it, and the other one would be completely right.
yeah, probably.
That was super branded for them. That would be cool.
Ema and Amanda would just be smiling. Oh, this is awesome.
Yeah. Then you look at it like, this is actually what you're going to do, though.
Yeah.
Good luck.
But actually, give yourself a few years.
The Saha equation. Saha. It is. So this is Meghnad Saha. $1920. That's exactly what I was trying to do.
Magna.
Yes, AD. Yes, Meghnad Saha, 1920. So he beat me to it.
Yeah.
Damn it. Yeah.
So,
Yes. It is the number of atoms in ionization stage I plus 1 divided by the number of atoms in ionization stage I is equal to 2, which comes from the fact that there are 2 spin states for an electron. The fact that the electron will spin up or spin down is what turns out to be responsible for that too, times the partition function for ionization stage I plus 1 divided by the number density of electrons, the number of electrons per unit volume, times the partition function for ionization stage I, times the mass of the electron times kT divided by 2 pi h bar squared to the 3/2 power, times e to the minus chi sub I over kT, times 1.
As you will go over to the show for homework.
Yes, I should joyfully still on the homework. Read this stat book and then prove the following.
you Thursday.
Yes,
It's actually going to be a question on the exam, so I suggest you get cracking.
yes.
We won't have time here.
So where Ni equals number of atoms, oh, this gets a box, kind of an important equation. That's the Saha equation. Ni is number of atoms in ionization stage I implication, I plus 1 is the number in ionization stage I plus 1, and Ne is the electron number density. In other words, instead of kilograms per cubic meter, it's the number of electrons per cubic meter. It's the density in terms of the number of electrons. Number of electrons per cubic meter. So we're not deriving this, but let's explain kind of, plausibly, what does it mean? So without trying to derive it, well, how do we interpret the different pieces of that equation? And then we'll do a lovely example, which will allow us to show why hydrogen lines should be strongest in stars at temperatures near 10,000 Kelvin. We'll understand why, even though hydrogen is far and away the most abundant element in all stars, that the hydrogen lines are actually weak in very hot and very cool stars, even though there's lots and lots of hydrogen. Essentially, it's because there's hardly, well, there's always hardly any, but there's really, really hardly any electrons at n equals 2 able to make Balmer lines unless you're in the magic temperature. And then it goes from hardly any all the way up to hardly any, and you get the strongest possible hydrogen lines. So, things to note. Note the extreme sensitivity to chi sub I, since it's up there in that exponent. So, doubling chi sub I does a lot more than cut in half the population. Right? There's an exponential relationship there. Note the extreme sensitivity to the ionization energy of stage I, since it appears in the exponent. And furthermore, note that what this is saying is, if I increase chi sub I, what happens to, not that you can, but imagine you had a dial where you could increase chi sub I, you could make an atom harder to ionize. What would happen as a result, all else being equal to the number of atoms in the next ionization stage? Would it increase or decrease if I make chi sub I bigger? It would decrease. And that makes sense. The harder it is to ionize, the fewer of them will be ionized to the next ionization stage. Increasing chi I means fewer atoms are in stage I plus 1. Since it is harder, strip off an electron from stage I. So from that standpoint, while we're not seeing why it's e to the minus chi I over kT, it has the right behavior you would expect. If it's harder to ionize the atom, then you don't get as many ionized atoms. What's that?
So what if instead of calling them atoms, we call them atoms?
As in
the name atom.
atoms? That same thing, yeah. But it's atoms. Atoms really don't like being ionized. They totally do not get a charge out of being ionized.
It's just funny. I have in my memory, I have a friend named Adam from elementary school, and so whenever I'm reading ionized atoms, I just imagine my friend Adam being 8, and just some reason they electrocute.
Yeah.
I don't know why my brain goes there, but it just does.
So if he works for a union shop, Is he unionized atom or is he unionized atom? There are some questions we need to ask ourselves.
I remember my sophomore year, Zach Plater wrote that on the board. He's like, I think I know I'm going to be a physicist because when I see this word, I see unionized.
Yeah.
And I was like, I see unionized. And he's like, you're a politics person.
Yeah. You know, that's like the test. That's a good point. That's the test. Yeah. What do you see when you see this word? And it goes from there. Yeah. Yeah. In UC 160 yesterday, we were getting the results of our MBTI Myers-Briggs type indicator test.
Oh.
So I worked out to be INTP, which is a very sciencey type of thing to be. You know, it's like in the list of you know, jobs that I should consider. Number one was like biological or physical sciences. I'm like, okay, this looks like I chose wisely.
What was the title of it?
What's that?
Did they have a title associated with each one? What was the title?
It just said it generically, like biological, physical, or something sciences.
Like, for when I took the Myers-Briggs test, we had this, like, a week ago, we all in the house went through it because we had this conversation of whether or not it was valid or not. And just sort of, but it's, I got the chem and I forget which system of letters that corresponds.
Yeah, there's 16 different combinations, because there's 2 times 2 times 2 times 2, yeah. Right, yeah, that's of course the big question is this BS or not?
I mean, historically, it's BS, but I mean, I think it's probably been like tweaked in such a way that it has at least some form of validity.
Mm-hmm.
But
yeah, right. But careful studies are really needed to verify.
Yes.
And I don't know if it does. I don't know. I'm not an expert on it.
No.
So, but where was I going with that? Oh, anyway, but it was funny because so one of them was like so like the students in the room, the ones who got the things that say like you should be a scientist, you're a careful observer and all that, versus the ones who are like intuitive, creative, whatever.
Mm-hmm.
He shows a picture of like this house in a thunderstorm with like bats flying around, and he just prompts everyone, like, tell me what you see. And it was funny because I'm looking at it, and I see lightning flashes, I see rain, I see bats, I see the house. And so that's what I'm thinking, and some of the students were saying things like that. And the ones who are like, the creative types or whatever, are saying things like, it's Scooby-Doo's house, it's Hogwarts, and coming up with whole totally unsupportable backstories. So
there's rain, bats, and a house.
Yes.
Not Hogwarts.
Right. So it's kind of interesting. I mean, I think that there's certainly hard differences in the way people think, Whether that's accurate in measuring them, I don't know, but
It certainly is fun.
it certainly is fun, that's right. Back to our story.
Sorry.
Yes.
Are you taking it?
I typed it in and it was like the first link, so
The one from the actual website for the test takes like a half hour.
Yeah, this was like 15, 20 minutes. I was being very freewheeling, I figured if this is really going to mean anything, I shouldn't be thinking about these answers. I should just be gut reaction and bling, bling. Yeah, bling, bling, bling. I mean, I wasn't just like randomly, but in other words, I wasn't like, I don't know, what would I really do in that? I don't know. I was just like, yeah, this one, I figured that's probably more accurate than trying to, figure it out. Notice that as t increases, what happens to this ratio? So as t increases, chi I over kt decreases. So e to the minus chi I over kt, if it's e to the minus a smaller number, gets bigger, right? E to the minus 1 is bigger than e to the minus 10. So the temperature, and then T, this obviously increases it too, that's T to the 3/2. Both the temperature terms say that it increases as T increases. Is that what we would expect? If the gas is hotter, would you expect more ionization?
Yes.
Yeah. Physically, you would say more violent and more frequent collisions mean more ionization. So from that standpoint, the equation says what you would think it would. not details where that your intuition doesn't tell you it's t to the 3 halves e to the minus chi over kt, but your intuition does say as t goes up, so does mi plus 1 over 9. Increases, and I plus 1 over and I increases as we would expect. This will be where we take our break. Since higher t says more frequent and more violent collisions. Or in other words, more ionization. So that works out, that's sensible that that happens. Break time.
Oh, you want to go there?
Can I take this, please?
Oh.
Can I finish this, please?
Now that